All right, this is 2013 from the BC exam, number 5. I had some requests to do a differential equation including an Euler's method. So we'll go ahead and get started on this one. So you can see you're given the differential equation dy dx, and you are also given an initial condition. So it says in part A to find the limit as x approaches 0, and it's kind of a different setup than we're used to seeing. So our goal here, remember, is always to try to plug in this x value there. So when I plug in that, I'm going to get f of 0 plus 1 over sine of 0. The problem with that is it's going to lead me to an indeterminate form. So I'm going to say the limit as x approaches 0 is going to be like f of 0 plus 1 over sine 0, okay? And that's going to be 0 over 0. So you'll see that this numerator goes to 0, this denominator goes to 0, which means you have an indeterminate form, so it is a candidate for L'Hopital's. So by L'Hopital, okay, that's going to equal the limit as x approaches 0 of the derivative of the numerator, right? So that's f prime of x over the derivative of sine is cosine x. So then from there, we can go ahead and plug in x equals 0 there. So I'm just going to go down here. So we're going to say that's going to equal the limit as x approaches 0 of f prime of 0 over cosine 0. Okay? And f prime of 0, so that means I'm going to go ahead and plug in. So when you plug in x equals 0, okay, so x equals 0 up here, you're going to get just 2 multiplied by, well, we know that when x is 0, y is negative 1. So you have negative 1 quantity squared by 0 plus 2 over cosine of 0 from your unit circle is 1. So we can go ahead and clean that up and get 1 times 2 over 1, and I get 2 for my answer for part A. So that was going to be worth 2 points. You got a point for applying L'Hopital's correctly, and you also got a point for the answer there. Okay, so in part B, it says, using Euler's method starting at x equals 0 with two step sizes of equal size, we're using it to approximate f of 1/2. So remember, with Euler's, I think that the best way to do it is to kind of set up this little table. At step 0, you have to put in your initial condition. So my initial condition, my x value is 0. My y value is negative 1, so I put that in there. The x row is usually the easier one. So if you're starting at 0 and you need to get to 1/2, okay, with equal step sizes, then my step size is going to be a quarter, okay, right? So a quarter here, a quarter there would get you to 1/2. And then the y part is what you need to do your kind of scratch work on. So remember, you use the previous, so it's negative 1, plus the step size, which was 0.25, multiplied by the derivative evaluated at that previous point. So you might need a little side work. And you'd say something like dy dx evaluated at 0, negative 1, right? Which we kind of already did above, but just in case, so you've got that negative 1 squared, and then 0 plus 2. So we know this is going to be 1 times 2, so it's 2. You take this 2 and pop it in right over there. Okay? Now, for the next part, you're going to use that. Well, we have to kind of add this up, so that gives you 1/2 minus 1, so that's negative 1/2. That is my output at x equals a quarter there on step 1. So now I use this over here, so it's negative 1/2 plus the step size was 0.25, right, multiplied by the derivative evaluated at this previous point. So my little side work, my derivative evaluated at 0.25 comma negative 0.5, something like that. So you can go ahead and do that calculation. Okay, so you're going to plug in the previous point into the derivative up here. Okay, so you're going to have the y squared, so you have this negative 1/2 squared, then multiplied by 2 times x, so 2 times a quarter is 1/2, and then plus 2. So really you have a quarter multiplied by 2.5, which is 5 over 2. Okay, so that gives you 5 over 8. Again, once you evaluate the derivative at the previous point, you take that 5/8 and you plug it in here. That, by the way, is your safe stop right here. If you felt like you needed to go further, you could, right, because this is a fourth, so you'd have negative a half plus, and then 1/4 times this would be 5 over 32. And then you'd, of course, have to turn this into 30 seconds, so it would be negative 16, right, plus 5, so negative 30 seconds, so negative 32s. I would highly encourage you to kind of safe stop it right at this point right there. And I believe that was worth 2 points as well. You get a point for applying Euler's and then a point for the answer. And then that brings us to Part C. Part C is kind of the traditional separation of variables that I think you are definitely going to see. It very frequently comes up as the common question that you'll get your points for AB for. So in Part C it says find the particular solution to the differential equation given that initial condition. So you got to kind of go all the way back to the top. What you'll notice, this is a differential equation because you've got x's and y's on both sides. The first thing you want to do to get any points for this is you need to separate your variables, meaning that your x's need to be with dx's and your y's with your dy's. I would probably start by multiplying both sides by dx and then dividing by y squared on both sides. So once you get to that point, okay, you'd end up with, so if you divide, so you'd end up with dy divided by y squared, that's getting all my y's and dy's on the left-hand side, equals, and then I'm multiplying the other side by the dx. So I'd have something like this. That's going to get you a point right there just for separating your variables, okay? And now your goal is to integrate. But before I would integrate, I might rewrite this as y to the negative 2 dy equals 2x plus 2 dx. And now you're going to integrate both sides. So we're going to integrate this and integrate that. I'm integrating the left-hand side with respect to y, and I'm going to integrate the right-hand side with respect to c. So add 1 to the exponent, divide by that number. Add 1 to the exponent, divide by that number. There's a terrible time for my felt pen to die on me. Okay, and then over here, you're going to add 1 to the exponent, divide by that number, right? So those 2's kill each other off. And then here, I would just tack on an x. Don't forget, we integrated, so we're going to have a big old plus c on the end. You can technically have a plus c here and plus c there, which is still just some other constant. I would probably take another line of work to kind of simplify this because I know I'm going to have to work with this. So this is the same thing as negative 1 over y equals x squared plus 2x plus c. Okay, so I've got that here. And now this is where the, you kind of have two options. Usually, if there is an e in here, or like if there's like an ln and I know I'm going to need to use e or something, I usually solve for y first and then apply my initial condition. But here, since there's no ln, there's no e floating around, I actually think it's smarter to apply your initial condition first. So to make sure you get that point there. So apply x equals 0, y equals negative 1. That was my given initial condition, and I'm just going to scoot my work up here because I'm trying to fit it all on this page. Okay, so after I apply that initial condition, you get negative 1 over negative 1 equals 0 squared plus 0 plus c. In other words, your c value here is positive 1. Once you solve for your initial condition, take that c and plug it back into that previous line of work before you applied it. So you've now got negative 1 over y equals x squared plus 2x plus 1, because that was what c was, so I'm just replacing that. And now your last point is going to be solving for y. So to get y by itself here, I would almost think of this like a fraction. Cross multiply. So you have negative 1 equals y times this whole thing. Okay? And now to get y by itself, just divide. So divide both sides. So you have negative 1 over that whole mess, x squared plus 2x plus 1 equals y. So now I have solved for y. Make sure that you're not supposed to do anything else with that. Sometimes they'll have you kind of, for an additional point, they'll say, use that to approximate something. But here, I answered the full question, so that's my final answer. If you really wanted to, you could factor that denominator, but I wouldn't risk an error there. So that would be where I would say stop it.